Some of the questions that were left on 2B. First of all, it says, does it make sense that a beach ball would have 10 grams per cubic centimeter? Okay. So what is the density of water? Well, that's 1 gram per centimeter cubed. So if a beach ball was 10 grams per centimeter cubed, then it would be 10 times as heavy as water. And I don't think a beach ball would be 10 times heavier than water, so this does not make sense. Okay. 16. This one was the speed skydiver, 614 miles per hour, and we're supposed to figure out how many feet per second. So we would have to get the miles to disappear, and change it to feet. So put the miles in the denominator to cancel the miles in the numerator. And 1 mile is 5,280 feet. Now our units would be miles per hour, or feet per hour, and we need the feet per second. So we need hours to disappear, so we'll put hours in the numerator since this one's in the denominator, so they will cancel. And I'm going to do it in 2 steps. I'm going to go to minutes and see 1 hour is 60 minutes. Now I'm down to feet per minute, and then I need to go get the minutes to drop out and get seconds. So I'm going to get minutes to cancel, and 1 minute is 60 seconds. So my answer would be 614 times 5,280 times 1 times 1 over 1 times 1 times 60 times 60. If I type that into my calculator, I could do each line separately, but on this kind I can use parentheses, and so I'm going to do 614 times 5280. That's my numerator. So I'll put that in parentheses. So I need to go back here and insert a parenthesis. Divided by, and then I have to start the denominator with a parenthesis, and 1 times 1 times 60 times 60. I don't need the ones because 1 times anything is itself. Enter, and it's going 900 approximately feet per second. Okay. On 41. So a runner uses 100 dietary calories, capital calories, per mile. 10 minutes to run a mile, and it goes for 1 hour. So there are 6 10-minute periods in an hour, so it's going to run 6 miles. So times 6 miles means they're going to burn, that way the miles cancel, and it'll be 6,000 calories. All right, but they want the power. And if we want it in watts, it's got to be joules per second. 6,000 calories, and that would have been in 1 hour. Okay, so yeah. So it's no longer equal. This gave us 6,000 calories, but it was in that 1 hour. So now we have to change it to joules per second. So this is dietary calories. So now we have to make it small calories. So that would be in a capital calorie. there's small calories of 1,000 of them. So now we got it into regular calories. And then we have to convert the calories to small calories. And so I got to put it in the denominator to cancel the numerator. And get joules. And there's 4.19 joules in 1 calorie. All right, so now we got joules per hour, but we need joules per second, which is what, a watt. So now we have to change the hour. So we're going to multiply by, let's put hour on top, and minute. So 1 hour is 60 minutes. And then we have to get rid of the minutes. So I put it on top to cancel the denominator, and the hours are canceled. And get seconds. So 1 minute is 60 seconds. Get that right. So we're going to multiply 6,000 times 1,000 times 4.19 and divide it by 1 times 1 times 1 times 60 times 60. So the numerator, parentheses, 6,000 times 1,000, which is a million, times 4.19. Oops, I didn't get times, I hit divide. Times, there we go. That's the numerator. All that, close the parentheses, divided by, open my parentheses, 60 times 60, close parentheses. So it's 6,983 watts. Joules per second, which is what a watt is. Okay? Or 6.983 kilowatts if you wanted to change it. Okay? All right. 45. A cube of wood is 3 centimeters by 3 centimeters by 3 centimeters and weighs 20 grams. So its density is what they want. Well, that's how many grams, which is 20 per cubic centimeter. Well, if it's 3 by 3 by 3, there'll be 3 across, 3 rows of them, so there's 9 on the bottom, and times 3 rows of 9, so there's 27 cubic centimeters. So its density is 20 divided by 27, which is 0.74. Now, just for reference, water is a density of 1. So this wood is lighter than water, so it would float. Okay? 53. So in this one, a lady is drinking glasses of wine, and each glass has 20 grams of alcohol per drink. She drinks 2 drinks, so she's going to have 40 grams of alcohol in her. And her the amount of blood she had, she was a smaller lady, so they said that there was 4,000 milliliters, 4 liters of blood. All right. So now we have to get this to be grams per 100 milliliters. So first of all, what's this work out to be? Well, 40 divided by 4,000 is 0.01 grams per 1 milliliter. But blood alcohol is per 100 milliliters. So we have to multiply the numerator and denominator by 100. 100 times this is 1.0 per 100 milliliters, which means the blood alcohol of this, the blood alcohol percentage would be 1. Now, a blood alcohol of 1, a person would die. So, and we know that somebody drinking 2 glasses of wine doesn't die unless they have some kind of allergy or whatever. And that's because they were assuming that all 20 grams of these drinks went straight into their blood. But that's not how it works. Your body takes a while to assimilate, for the alcohol to get into the blood system. It takes, maybe the 2 drinks might take 2-3 hours before all the alcohol gets into your system. And as soon as it starts going into your blood, it starts, your body metabolizes it. It uses that alcohol up, so it's no longer in your blood. And it does that at 10 grams per hour. So this person won't die, but if we assume that it all went immediately in, then they would die. Now, the second scenario, part B of this, said what would happen to the blood alcohol rating if all of it went right straight to her blood, which is not correct, and then it lost in 3 hours, every hour losing 10 grams. Well, in 3 hours, it would lose 10, 20, 30 grams. Started with 40 grams, so now there'd be only 10 grams left. And her blood volume is 4,000 milliliters. So if we divide those, we get 10 divided by 4,000, which is 0.0025 grams per 1 milliliter. But the blood alcohol is per 100 milliliters. So once again, we need to multiply by 100 and by 100, and multiplying this by 100 becomes 0.25. Now, if the blood alcohol all went straight into her system, and then for 3 hours later, this is true that it goes 10 grams per hour, the blood alcohol rating would be 0.25. And a blood alcohol content of 0.25 is legally drunk, but is not lethal, not deadly. And that's how that problem works. 55. So it says, find the men's average speed if they ran the regular mile, which is 1,600 meters, or the metric mile, which is 1,500 meters. So let's do it the speed. Okay, the first question was, the metric mile is what percent of a mile? So metric mile, 1,500 divided by 1,600 is, changing that to percent, we multiply by 100, so it'd be 94% rounded off, 93.75, 94% of it. I'll write it down here, 93.75, because we're going to use that later. Okay, now the men's average speed. Let's do it in meters per second. So this says 3 minutes, 43 seconds, 43.13 seconds. Well, 3 minutes times 60 seconds in a minute, times is 180 seconds. So the men's pace, average speed is 1,600 meters in 180 plus 3, 180, no, plus 43, plus 43.13, 223.13, 223.13 seconds. So their pace for the regular mile is 1600 divided by that answer. 223.13 divided by, no, clear. 1600 divided by 223.13 seconds is 7.17 meters per second. Now for the metric mile, their average speed would be, so we got down here for the metric mile for the men would be 3 times 60, 180 plus 26, that's 206. And the metric mile is 1,500 meters divided by 206.00, which is 7.28 meters per second. So on the, did I do that right? Oops, quit. See, it was 180 plus, I'm having trouble hitting the right buttons here, plus 26. I hope I've copied this right. Let me check that. 55. 326, yes. 26.00. So 206, 1,500 meters divided by 206 seconds is 7.28. So, that's right. So that speed is a little bit higher than for the 1,600 meter. Now that sort of makes sense because if you're running 1,500 meters, you won't get quite as tired as if you're running 1,600 meters. A little longer race means you're going to get a little bit more tired and probably have a little bit slower pace. And that's what it is, a little bit slower pace for the regular mile versus the metric mile. That's true for the men. Now what's true for the women? So we're going to do the same process here, but we got different numbers. So we're going to have a 1,600 meter race divided by, and now we have 4 times 60, 240 plus 12, 252.56 seconds. So their pace is 6.34 meters per second on the regular mile. Slower than the men's regular mile and slower than men's metric mile. Now let's go to the metric mile for the women. So that would be 1,500 divided by, now we got to do 180 plus 50. 180 plus 50 is 230.46. So that is 6.51 meters per second. And again, let's see here. 180 plus 50 is 230.46. So, and 1,500 meters, so 6.1, so wait a minute. 6.5, and the other one was 6.3. So the woman's metric is slower than their regular one, which is kind of a surprise. Okay? So now they say, what would be the new records if they ran the faster pace for the whole 1,600 meters? So they would now have to run a longer race. So if they did this many meters per second, then we want to find out what their times would be. So we'd put the seconds on the top, and 7.17 meters times a race length of 1,600 meters instead of 1,500 meters for the whole race. And so the meters would cancel, and we'd have 1,600 divided by 7.17, which turns out to be 223.15 seconds. So if we take out the 180, 3 minutes, that would leave 43.15 seconds instead of 108. Yeah. 1,600 divided by 7.17. Yep. So it would be pretty much the same, slightly more. Did I do the right ones here? No, I wanted to divide by the faster pace, 2.8. That's what I did wrong. So I want to take 1,600 divided by the faster pace, 7.28. Enter. So that's 219.78 seconds, which would be, if I take 180 out, it'd be 3 minutes for the 180. And 180 from that would leave 39 seconds, roughly, 39.78. So it would be like 4 seconds faster if they could keep this pace up for the whole 1,600 meters. So it would be tough to shave off 4 seconds. And you do the same for the women's. Okay, now the final problem. This one said that we have a windmills producing 200 kilowatts of energy, and it's going to run for 1 year. So we want to find out how many kilowatt hours. So we want to take 200 kilowatts, kW, times 1 year. But we want kilowatt hours because at home they measure in kilowatt hours. So we got to figure out how to change years to hours. So 1 year, put that in the denominator because this is in the numerator. And 1 year is 365 days times, and then we got to change days. So those cancel. And the days is how many hours? Well, that's 24 hours. So we get 200 times 365 times 24. And so we get 1,752,000 kilowatt hours. And those are times each other. Now, if a house uses 10,000 kilowatt hours a year, We would divide that by 10,000 to figure out how many houses it would run for a year. And that'd be 175.2 homes. Okay? And that is 2B.